So last week we talked about, we were working with the Star Wars data set. This is an example data set. We were running we looked at the data and we did some correlations on the data. We did some histograms. We used core tests to look at Pearson and Spearman correlations. We did a simple linear model where we compared mass and height. And we looked at the residuals of the data of that model. And we plotted a line, or the sort of the linear prediction between height and mass. And that was the end of the last lesson. So what I would like to talk about—
quickly review the prediction part of it, like the very thing we did at the end.
Oh yeah, let's quickly review the prediction part of it. That's a great idea. So we had our model, which we called mod. And to do the prediction, I basically made a new data frame, right? So we had a data frame with basically all the possible heights. So I went from the height of the shortest person to the height of the tallest person. And I used the predict function. Predict function says, okay, give us a linear model and give us some height and mass, or if not some mass data, just some height data. And then we'll use that height data to try to predict the mass data, because that's what the model does, right? So the model took height data to predict, the model, we trained it with some height data and used that to predict some other mass data. Here we're giving it new height data. I gave it just a whole range of heights. We could give it a smaller subset or even just one person and try to predict their mass. And so we have for every possible height what we think the predicted mass was. And then, and that was that was our prediction. We stuck that all together as one data frame. And then we plotted the actual data with ggplot. We have our height and our mass actual data, and we used points to do that. And then we also did, for our predicted data, for all the individual predicted heights, we also did all the masses versus all the heights. And because the linear model gives you essentially a line for every one of our heights, it gave us one point and it connected all this together with the line, which is why we had this nice green line going through all the points. Does that connect?
Yep, thanks.
Cool. All right, so let's talk about, so here, mass and height are both what we'd call continuous numeric variables, right? So they're all on a spectrum between one value and another. In fact, they happen to be somewhat normally distributed, which makes our statistics easy. But most of the data, if we look at the Star Wars data set again, are not nice continuous data. Most of them are categorical data, right? So we've got hair color. Some people don't have a relevant hair color, but some people have different hair colors. Some people have skin color, some have eye color. Birth year is categorical. Gender, of which there are 3, 4 if you count NA, male, female, none in NA. Homeworld, there's a bunch. Species, there's a bunch. And then there's even more complicated types of data like films, which are actually a whole list of different things. But so let's say we want to use species, and we want to look at whether species relates to mass, right? So you can't just stick species into your standard linear model, because linear model expects things to be on some sort of spectrum. But we can deal with them. So let's say, and let's make our job simpler for us. Instead of saying, we want a linear model that predicts all the species. Most of our species only have 1 or 2 characters in them. So let's just say we want to predict whether, or actually we want to use whether somebody is human to try to predict their mass. So I want to make a new variable using the mutate function. And we talked a little bit about what mutate does. And so I said, I'm basically going to say that if a character is human, we want to put yes for their species. And if a character is not human, right, so that would be droids and Ewoks and whatever Jabba the Hutt is, although I think we omitted him as an outlier earlier, and so forth. If they're not human, they're going to give them a no. And so that this if-else expression lets us do that. So if it's a human, yes. If it's not a human, no. And now what we're going to do is we're just going to plot, just before we even run our linear model, we're just going to plot whether people are human against their mass. So here we have our data, right? So we've got a bunch of characters who are not human, and they seem to have a pretty wide range of masses. And we have characters who are human, and they sort of seem to have maybe the smaller range of masses, right? Which makes sense. They're just one species. They tend to have a narrow range of differences. And one person who does NA on whether they're human. Wonder who that is. And the question is, one thing we can ask is, if we look at the yes and no's, is there sort of a linear relation? You see, maybe it looks like maybe the humans are a little bit, on average, a little bit more massive than the non-humans in the Star Wars universe. And we can test that with a linear model. So the way that essentially works is that we just feed it in the same way we feed everything else. So we've got mass versus is human, and we run it, and we get this model out. And let's just talk a little bit about what this output means. So as you recall, if we go back, we did mass versus height. We have a very similar kind of term, right? So we have our intercept. So this is essentially saying that if people had a height of 0, this is what we'd expect their mass to be, which isn't super useful, and this is their height. So if we had an equation that was y equals mx plus b, we'd say mass is negative 32.5 plus 0.62 times the height. So let's go back down here, and we have our linear model. So we've got our intercept and our slope. So what we're saying is that if they are human, we give that a 1, and if they're not human, we give that a 0. So basically what we're saying is that the height or the mass of a person, of a character, is 71 plus, let's do 71 plus 11 times 1 if they're human, right? So that's 1, or 83. So we're saying humans have an average mass of 82. And for non-humans, it would be 71 plus 11 times 0, right? Here's our 71 plus, this is 11 essentially, times 0, and that's going to be 72. So we're saying that non-humans have a mean mass of 72, humans have a mean mass of 83. And that's essentially all that linear model is telling you. It also tells you whether it's a statistically significant relationship. And in this case, this p-value is about 20%, which is to say that it's statistically likely that that relationship that is emerged essentially due to sort of random factors. It is not necessarily real. And so that's how you do a linear model with one categorical variable that is essentially either yes or no. Questions about that? So we can do the same kind of thing with gender, right? So we've got, here's, oh wait, no, these are, so we've got species and gender here, right? So we've got is human males and females, and what you can see is that, at least for the humans, the males appear to be a little bit more massive. Oh, here's the one that, oh, Slime-Ore does not have a species. So right, so here's our human males. Our human females tend to be a little bit less massive. With other species, that's maybe less clear, which I guess makes sense. And then we can say, okay, well, let's say we want to run a linear model where we have both the characters, I guess they're calling it gender in this data set as opposed to sex. So both the characters gender and whether they are human or not. So so we'll say, are they male or are they human, and what's their gender? And since there aren't very many characters, there's only one character with no gender, so we're going to not include that one in this analysis just because it's going to be statistically, we're not going to have any statistical power to deal with that particular character. We're going to remove all the ones that have NA for gender. Same with NA for species. And so we're just going to look at so we're going to subset this to the male and female characters and just to the human and non-human characters. And then we can run, once we've done that, we can run our analysis. And so it's this very similar setup. We say mass is related to whether they're human and their gender. And then we get something that looks like this. So now we have a couple of terms. We've got our intercept. Again, we have whether they're human and whether they're male. And so you can imagine this as another kind of equation. So we say that if we have a human female, that would be 52, that's our intercept, plus 9 times 1. So that's our coefficient for whether they're human, and they are human, so they get a 1. And they're female, so they get a 0 for being male. So we say it's going to be 51 plus 9 times 1 plus 25 times 0, and that equals 52 plus 9, 61. I think I got that right. And then we can look at our p-values and say, well, our p-value for the whole model is less than 0.05, so it's probably the model as a whole is working. And it looks like the male category, whether they're male, does seem to have a positive effect on mass, right? So men tend to weigh more across the whole data set, but humans, it seems to be less of an effect. But you might say that, well, you know, when we looked at this, the this plot up here, it looked like there was a real clear difference for humans, but maybe less so for other aliens. So I want to say, is there an interaction between humanness and gender on mass? So we can do an interaction term. So here we'll say, instead of doing gender plus, gender plus species, we're going to do gender. Oh, in this case, I'm actually doing, we're gonna do gender times height instead of gender times species. So here we have our intercept, whether being male seems to relate to that. So we say, and then we have height, and then there's an interaction term between the two of them. So we can, that's another linear model where we say whether, so if this was to be statistically significant, we'd say there's an interaction term between males and height. So we'd say that, like, for males, we tend to see height as more of a relationship on mass, and females it is less, or something like that. Actually, in this case, that is what that says. Although it's not statistically meaningful in this particular case. So here we have a bunch of terms, none of which have an effect. But we could do this with gender and species. Here I wanted it to be a discrete variable for some reason, but if we didn't. So we'll do gender and is human. And here we can say that there isn't. So this would be, if this were statistically significant, we'd say that humans appear to have more of an effect of maleness on mass, and non-humans have less of an effect of maleness on mass, which sort of drives what we were saying, but it isn't a statistically meaningful interaction. Only maleness appears to relate to mass. Are there questions about any of that stuff before I move on to logistic models? Anyhow, in a logistic model, we essentially just we flip it around. So now what we're trying to do is, instead of predict the mass from, say, whether somebody is human, we can try to predict whether somebody is human from their mass. And that actually might be more meaningful, right? Because we go back up here. Right, we've got our humans and our not humans. And you can say if somebody's like has a mass down here at, like, 30, they're probably not human, or, way up here at 160, they're probably not human. But if they're in the middle, they're maybe more likely to be human. So we can start to articulate that. Let's just start with a really basic logistic regression. That's probably not going to be right. So we could do, well, the first thing that I want to do, so logistic regressions is their y variable like it to be coded as ones and zeros as opposed to say yes and no. So I just recode that here. So I say if is human is yes, it's a 1. If not, it's a no. Save that to another thing we're calling Star Wars 4. And now we're going to do our linear model. So it's basically set up like LM, except as a GLM. You can actually do a GLM of your standard linear model. We could do the last model as a GLM as well. What we're doing here is we're setting the family to binomial. So that's saying that our y variable is a series of ones and zeros as opposed to a continuous variable. And we run this GLM and we look at the model, and after we run it. And here we can say is that mass, in general, more massive characters tend to be human than less massive characters overall. But we're forcing it to be linear. We say it's not really a statistically significant interaction.
I have a question.
Yes.
So you're doing this, you have is human, yes or no. You couldn't do that, so it's 0 and 1. You couldn't do it if there was like a third or fourth category, could you?
Nope, you can't.
Okay.
To my knowledge. So there's other kinds of, I mean, if we want to start getting into like predicting more categories, we can do that. But the way that I would generally set that up. So we start getting to more categories. There are probably other models that would be appropriate to try to predict something in a multi-categorical space.
Okay.
But what you can also do is you can set up a bunch of linear models. So let's say we have, we've got, let's say there were more Ewoks, right? So we've got humans, Ewoks, and everybody else. So we could do a logistic regression to predict whether somebody is human, and then we could do a second logistic regression to predict whether they're an Ewok, right? So is human, yes, no, run the logistic regression. Do another one, is Ewok, yes, no, run the logistic regression.
Okay.
Yes, and that would probably get you your answer. So I mean, then you could have a character that's likely 75% likely to be human and 25% likely to be to be Ewok, and then there's sort of a remaining kind of thing too. So that also works.
Okay, thank you.
What I'm going to get at now, though, so we said that a linear relationship between mass and whether somebody is human doesn't really seem to make a lot of sense because the human mass is sort of in the middle. So we can actually do a what on earth? I wonder what I did here. So this is the outputs, right? So I did the same prediction function that we did before, and so here we have humans up here, non-humans down here, and what the model is saying is this line here is the probability that a character is human as the mass changes. So we say the characters over here are more likely to be human, ones over there are lower mass characters are less likely to be human. This doesn't really work with experience because in general it seems like if you're 160 kilograms, you're probably not human, really, right? Because this character down here isn't. So this linear relationship doesn't really seem to fit. So what we can start to do is to say, well, what if we say this maybe could be a parabolic relationship? So we can put that in like this. So here we have the same GLM and we have our same mass term, but now we put a second term, which is our mass squared term. So we're going to say that whether something is human is a function of both their mass and the mass squared. And so that ends up looking like this. We say here's the mass term, here's the mass squared term. Those both seem to matter, which is to say that in general, there's a positive relationship here, but also mass squared. This is negative, which means there's some sort of nonlinear thing going on. And instead of just trying to interpret what this means exactly, well, basically, this is fit by a parabola, and it's a parabola with a negative second degree term and a positive first degree term, which is going to be a downward facing parabola. So you can actually look at the results like this. So here we've done the same kind of prediction, and here we have a sort of a parabolic relationship. So characters with intermediate mass are most likely to be human, and characters with extreme masses are less likely to be human. And this sort of fits with our experience, right? So if our mass is, say, 90 or something, we can be as likely as 60% probability of being human. And as we get out to these extremes, our probability of being human starts to approach 0. And that's it. That's all of the lesson on logistic and regular regressions for categories. Any questions about that you want to ask on the record? One thing I'll point out is one thing that trips me up every time is when I put in the mass squared term, you have to surround it with this I thing, which says is an identity, which essentially says you want to actually take the mass data and square it and put that in as a term. If you just do mass squared, it for whatever reason ignores it.